So far, we have talked about the conventional electrical measurement technique for PD. So in the conventional measurement technique, we try to register the pulse that is produced, the current pulse that is produced due to partial discharge happening inside an equipment, and we try to measure that using electrical circuits. But we have also seen that there are various problems associated with such measurements. Most importantly, we have talked about a very low signal to noise ratio, a lot of noise, a lot of interference. And one of the most important problems that we have not talked so far about is location. So when PD happens, we would like to know the magnitude of the PD that is taking place. So we would like to detect the PD. That is the first thing that we need to do. And no doubt about it, that is an important achievement. And that is an important objective. However, if you need to take corrective action, it is not enough, especially when you're dealing with power equipment, which can be very large, which can span over a large area. It is most of the time not sufficient to just be able to detect the presence of PD. In fact, most of the time you will have PD. And the magnitude of PD is not really a very meaningful quantity unless we know from which location the PD is traveling to the sensor, because as the PD travels over a large distance and through different complex equipment or components, there will be considerable attenuation. And so a small magnitude may not necessarily mean a small PD. It depends upon the location. So what I'm trying to say is that it is not sufficient to just be able to detect the presence of PD. It is very important to be able to locate the PD so that you know where the PD is taking place, and if PD of a certain magnitude at that location is dangerous and needs corrective action, or if the magnitude of the PD that you're measuring is low simply because it has traveled a long distance and not because it is a small PD of innocuous magnitude. So the location of PD is very important, and the conventional electrical PD measurement techniques really provides us with no means of locating the PD inside a complex equipment. And therefore, what we try to do is we try to look at alternative techniques, which may be electrical or non-electrical, so that we can estimate the PD that is taking place and decide on what course of action to be taken. The first technique that we will talk about is the Rogowski coil. In the Rogowski coil, let us imagine we have a current carrying conductor. This current carrying conductor may or may not carry any current. Imagine you have a balanced circuit condition, and under balanced circuit condition, no current flows through the current carrying conductor, or even if there is current, it is a steady current that is flowing through the conductor. Now, when a PD pulse happens, there will also, this is an external current carrying conductor in the external circuit, there will be a simultaneous PD pulse in this current carrying conductor also. Now, the Rogowski coil is an air-cooled coil which is connected around the conductor in a toroidal fashion. So as a result, when there is a current flowing through the conductor, there will be a magnetic field which will be produced, and there will be this magnetic field will cause flux linkage with the Rogowski coil, and as a result, when there is a PD pulse through this current carrying conductor, there will be a corresponding EMF induced in the Rogowski coil due to the magnetic field that is produced by the current around in its vicinity. Now, this induced voltage, which is measurable, this induced voltage, which we can find, this is VIT, this induced voltage in the Rogowski coil, now can be amplified and can be can be transferred through an integrating circuit, and this induced voltage integrated electronically will give us a measure of the current pulse, the total integrated current pulse. So if you remember, we are sometimes interested only at the peak of the current pulse, sometimes we are interested in the integration of the total current pulse. What is the total current pulse, total area under the current pulse that is needed, and that can be done using an integration circuit. So the Rogowski coil does not actually connect electrically with the current carrying conductor, it connects magnetically with the current carrying conductor. So this is one technique in which we measure PD. This is still an electrical technique, but it is not the conventional electrical technique. This is not what we mean by the conventional PD detection circuit. Next, we come to the antenna technique. Now, we know that when a partial discharge happens, the partial discharge gives off energy. When there is a current flowing, there will be I square R losses, so there will be heat losses, there will be light, there will be sound, there will also be electromagnetic radiation. The antenna technique depends upon measuring the electromagnetic radiation or the radio interference that is generated by the PT activity. So in the RF radio frequency range, the emission is measured with antenna in order to detect the presence of PT inside the enclosure. The quantification and characterization of the radio frequency noise is possible. The advantage of this method is that it is a non-intrusive measurement technique. You do not have to go inside the chamber to be able to measure. However, there is not a lot of work that has been done in this area, but there is some research in trying to use the antenna technique for PT measurements. Next, we come to the capacitive probe technique. Now, let us imagine you have an enclosure, and within that enclosure, there is a high voltage component and there is a resultant partial discharge. When this partial discharge happens, electromagnetic emission will take place from this discharge. These electromagnetic radiations will travel outwards from the origin of or from the location of the partial discharge, and it will travel towards the enclosure tank, the walls of the enclosure. Now, if this is metal encased, these electromagnetic radiation cannot travel outside. However, if there is any gap in this metal clad enclosure, the electromagnetic component, the electromagnetic wave can travel outside through this gap, and when it does that, it can react or interact with the earthed metalwork. There are earthing leads that are provided all around, that is at ground potential, and this electromagnetic wave can interact with that earthed metalwork and can produce in it what is called a transient earth voltage. This transient earth voltage can be picked up using capacitive probes. This is the advantage of this technique, is that it is a non-intrusive method. You can do the measurement from outside the metal enclosure, but just as in electrical measurements, the electromagnetic interference can also pollute measurements, and in this case also you do not have the option of being able to locate the partial discharge in space in any way. Now we come to a completely non-electrical technique, the acoustic technique. Now, when you have a partial discharge happening inside a metal enclosure, this metal enclosure may be filled up with some kind of a fluid. It can be a gas. Mostly it will be gases. It could also be liquids. Now, when a discharge happens, there is a burst of energy. There is a sudden burst of energy at a single point. As a result, a shock wave is created, much in the same manner as when you have a bomb explosion. And when this pressure, so it sets up, this shock wave sets up pressure waves in its vicinity, and these pressure waves in the fluid, and these pressure waves will travel through the fluid. They will radiate outwards, and once these pressure waves reach the metal enclosure, it will set up small amplitude vibrations of the metal enclosure. Now, if you have an acoustic sensor outside the metal enclosure, connected to the metal enclosure, any small amplitude vibrations that are set up in the tank wall due to the partial discharge inside will be picked up by the acoustic sensor. So that is the basic principle behind the acoustic technique, which depends on sound energy to travel from the position of the partial discharge to the position of the sensor. Actually, acoustic emission techniques came to be used quite casually when we were talking about corona. If you remember, corona is nothing but partial discharge happening in open air. Corona routinely happens in power transmission lines. And in fact, even today, you can hear corona happening. So the best detection technique for corona is often your ears. You can hear the sound that comes from corona, and a trained ear can very quickly pick up the characteristic sound that happens from corona. And therefore, just by manual listening, it is possible to, or catching the sound energy, it is possible to detect a corona. Of course, this can be improved upon. So directional microphones were used. These were operated at resonant frequencies in the range of 20 to 40 kilohertz. So they resonated an acoustic wave, a sound wave which is traveling from PD, is an impulse wave. Therefore, it has all a large broadband frequency range. It has a lot of frequencies. Now, you can choose to measure at a frequency band which you think is convenient for you, where the magnitude is high enough and where you expect the interference to be low. And that is what is done. So based on field experience, the frequency range of measurement is chosen to be 20 to 40 kilohertz, and directional microphones which resonate at these frequencies are used so that you hear an amplified sound. My parabolic microphones that are used for this purpose are called corona phones. Location is also possible, but in this case, you have to really depend upon the skill of the operator and what experience he has. In that case, he may be, just by trying to figure out where the sound originates, he may be able to locate the position of the corona. But of course, a corona is a visual phenomenon. It is in an open air, so location is much easier. Even then, when you're just depending upon the sound, the location or the detection of PD through these directional microphones or corona phones may be difficult under certain weather conditions, especially if you have a lot of wind, it may become difficult. Now, acoustic detection techniques came to be used with the advent of GIS. What are GIS? GIS are gas insulated substations. So, where you have the air insulated substation, where air plays the role of the insulating medium. Now, the advantage of air is that it is free and it is abundantly available, but you also need to provide large clearances, and especially with the kind of voltages that we are talking about these days, you need large clearances, and space is at a premium. So inside cities, inside crowded areas where you do not have control over the movement of humans or animals, then that kind of clearance may not be possible. And therefore, we have what are called gas insulated substations. We'll talk about gas insulated substations in greater detail later. Gas insulated substations use pressurized gas, most often sulfur hexafluoride, or some combinations of SF6 and nitrogen or other inert gases as the insulating medium. Now, since it is not air, you need an enclosure to contain the gas, especially if you're going to use pressurized gas, and that's what is used. So therefore, in a GIS, you have the advantage that you need a much smaller space, and they are more reliable because they are protected from the environment. But at the same time, since the entire thing is enclosed, any kinds of maintenance operation or any kinds of failure can be very costly. And therefore, it became very important to be able to monitor the condition of the GIS from outside regularly over a period of time. And that is when the acoustic emission technique for PD detection came into importance. Here you see one of the pioneers of acoustic emission, Grable. He used a commercially available ultrasonic contact. So he goes there with a stick and he keeps on tapping on the walls of the enclosure to figure out if PD is taking place. Of course, this depends very largely on the skill of the operator. A normal person will not be able to do it, and this does not have very good reliability. Uh, Actually, the electrical acoustic emission technique is very sensitive, but the problem with this is that the interpretation of the AE measurement techniques is an important issue, and it is not at all easy, especially in power equipment. One of the important things that happens is not so much in GIS, but in other equipment, but also in GIS, the acoustic wave does not only always have to travel through fluid. As long as it travels through fluid, there is not a lot of attenuation. So the magnitude diminishes, but not a lot. But if it has to travel through spacers, through solid materials, then there might be considerable attenuation. In fact, some solid materials may be even impervious to acoustic wave. They will simply block the acoustic wave and you will not be able to measure. The acoustic wave will not reach the sensor at all. But even if that does, remember we are not measuring actually the pressure of the fluid. We are measuring the magnitude of the small displacement waves which are set up in the metal tank. And these are flexural waves. Flexural waves are dispersive in nature. What it means is that different frequency components have different wave velocities and they travel at different speeds. So let us imagine at the location of the discharge, you put accelerometer B. An accelerometer B is a sensor which is a piezoelectric sensor which can sense the acceleration of the acoustic wave at a particular position. Let us say that accelerometer B is positioned very near to the partial discharge. So you see a wave like this. However, imagine the accelerometer A, which is positioned quite a distance away from the PD position. Now, the various frequencies will travel at various velocities. The result would be that a wave that looks like this, and that is what you're expecting at your sensor location, so that you can figure out what is the time taken to travel, therefore what is the location, etc., arrives like this. So the shape is no longer visible, there is considerable attenuation, and therefore you may not even be able to detect the wave because of the combined effect of attenuation as well as dispersion. Here I have some examples from certain experiments we've done in the lab. Here you see this is the kinds of signal that you would see at a sensor located on the vault tanks. As you can see, this has a broadband spectrum, and therefore it is possible to use any frequency bandwidth for measurement. We can see that at low frequencies the magnitude is very high, and the magnitude keeps on decreasing as we go towards the high frequency range. In this picture you will see some numerical measurements, numerical values, numerical curves which match the experimental curves. This is part of the research, and please feel free to ignore this. We are not going to talk about the numerical measurement, simulation here. These solid lines, these dashed lines are the experimental curves, and as you can see, these experimental curves are quite broadband, and so it's possible to make measurements in any range between 0 to 150. If you are at the low frequency range, there will be considerable noise, so therefore we prefer to make measurements at around 150. We can go higher, but if we go to, let's say, 200 kilohertz, the magnitude will diminish, and therefore the signal to noise ratio. The noise may also decrease, so we'll have to see whether the signal to noise ratio is what will decide you. If even with low amplitude signals, the signal to noise ratio is good, we can go to higher frequencies as well. This is something where the engineering judgment comes into the picture. If you look at the research on partial discharges, you will see that if you remember, even for electrical signals, I said that there are only certain techniques, only certain hardware techniques that you can use to filter out the noise. But there will be some noise still left, and then we have to employ software techniques for eliciting of the data in a better way. And one of the techniques that you will routinely see employed in the research on partial discharges is the wavelet technique. I will not go into the details, but I will tell you how wavelet analysis can help you in eliciting information from the wave, which can help you locate the discharge. Now, this is a wavelet transform, a continued wavelet transfer of the velocity signal. Now here, what you have here on the x-axis is time, and on the y-axis you have what is called scale. Let's not bother about what scale is. Scale is kind of corresponds to the frequency. So higher the scale, lower the frequency. So basically these are the low frequency components. 61 gives you a measure of the low frequency components, whereas 1 and 5 corresponds to the high frequency components. So in this case, what we have done is we have done an FFT of the velocity signal. What the information FFT gives us is that it tells us what is the frequency content of the signal, and that helps us decide on the frequency range of the measuring sensor. But in this case, we have additional information. We have the information about which frequencies will be available at which times. So as you can see, high frequencies are located in time, in a very small time. The high frequencies are located, and after that they're gone. Whereas the low frequencies persist for much longer time. And therefore, what we can do is, if we can do a high frequency measurement, we will not only be able to probably work with a good signal to noise ratio, we might be also be able to measure, locate in time exactly when this emission occurs, and that will give us a measure of what distance this frequencies have had to travel to the sensor, and because they are not spread over a wide range, we will be able to identify in time exactly when this emission took place, and from the time space correlation we will also be able to locate in space where the PD discharge occurs. So sometimes this kind of time information can be useful to us. Next, what we will do is we will talk about acoustic emission techniques used in transformers. We have been trying to attempting to use acoustic emission techniques for all power equipments, including rotating machine, but that has proved to be a challenge. But in transformers, also there is a lot of challenge involved, but in transformers, it is generally already used commercially. Commercial acoustic emission techniques for measurement of PD in transformers are available. Now, when you're measuring in transformers, you have to think about what are the factors which might influence the signal. One is distance of the sensor location from the source. If the sensor is very far away, remember we are talking about power transformers which are huge. And if you have sensors which are, you do not know the position of the source. If your sensors are so located that the wave has to travel a large distance, as you know, as we have already discussed, there will be a lot of attenuation, there will be dispersion, and there may be even blockage. There might be materials like the core or the windings which are actually impervious to acoustic wave. The angle of incidence of the pressure wave at the sensor, does it come and hit it perpendicular? Does the wave come and hit the sensor perpendicularly, or it comes at an angle? Will decide what is the magnitude of the signal that is picked up. The PD magnitude, if you have PD of very low magnitude, you will not be able to pick that up. Transformer oil has higher acoustic impedance than any gas. And there might be, as I said, acoustic barriers like pores or windings, which will prevent the signal from at all traveling to the sensor. So obviously we cannot work with one sensor. We will have to work with an array of sensors, and we will have to decide where to position the sensors so that we are able to we don't miss the PD at any particular location. So then we have to know, where do we expect the PD to happen? What are the sources of discharge in a PD? So discharges can happen in the open oil. So for example, inside the oil, there might be some protrusions from the windings. There might be corona discharges happening from protrusions. There might be sliding discharges on the surfaces. Because of the surfaces, there might be so this is when the discharge is happening in the oil, and the oil there will be pressure waves traveling through the oil to the metal enclosure. But the problem is discharge may occur within a confined surface. So where you have insulation inside the transformer, or let's say in a gas insulated substation, you have spacer. You also have similar interface, similar solid material inside the transformer, and inside the solid material there might be entrapped bubbles, and in that bubbles or in delaminations or in wedges, discharges might happen, in which case discharges may become much more difficult to estimate. Discharges can very likely happen in oil paper interfaces. So you use oil paper insulation in transformers, and where the oil and the paper, at the interface of the oil and paper, there is likely to be a lot of electrification. There might be space charge accumulation, and there might be, as a result, a discharge which is traveling along the surface of the paper. And these are called creep discharges. These creep discharges are also sources of, can be considered to be PD or partial discharges, which can ultimately lead to failure. So these are the three main components, three main sources of discharge in transformer. Now what we do is we use triangulation techniques. We use array of sensors on the enclosure, on the outside of the enclosure at various points. And we take the measurement, the signal that is measured at several sensor positions, and we use a triangulation technique to figure out what path might have been taken by each signal to reach each particular sensor. And so you have several sensors, and using them and using a triangulation technique, you can estimate a likely position of the source of the discharge. And since there are a large number of sensors, you continue these triangulation methods, you continue to obtain various positions. Now, these location algorithms are not very accurate, so that what would happen is you may not be with one measurement, with one triangulation, you may not be able to locate the exact position. So you have an array of sensors, you use the entire information together, and as you see, you get a concentration of positions here. So this is a three-dimensional image, XYZ plane, and you have one position, one region where many of these possible lines are agglomerating. So that is that. In that way, you can figure out that there is a very strong likelihood these might be stray signals, maybe inaccurate readings, but maybe where you have a large number of signals clustered together, it is possible that it is in that location that you have a major source of PD. Remember, it is always possible to have more than one source, but if we can locate the major source, the primary source, not primary source, the major source where the highest PD magnitude is taking place, that too can be an advantageous. Apart from acoustic techniques, we are also going to use certain other techniques where we try to look at the various other energy forms that are emanating from a PD, and we use measurement techniques to measure those energy contents to be able to detect and to locate PD. This we will discuss in the next lecture.